Welcome to the next video in our SimpleCPU Games Console video series, where we look at the video display controller's tile draw and tile overlay functions. Okay, so in the video display controller we have two tile commands. We have draw tile and we have overlay tile. The parameters you pass to these two functions are the same, so you pass it the address of the tile in video memory that you want to display, and then the X and Y positions where this tile will be drawn on the display. So this XY position denotes the top left corner of the tile, and that can be any pixel position. And finally, you pass these functions the color that the tile will be, so each tile is a single color. Okay, that raises the question, what is a tile? And a tile is an 8x8 pixel graphical element stored in the video memory. So you have a library of predefined shapes that you can draw on your display. So each tile contains 64 pixels, as I say, an 8x8 array. And within that, you can define whether that pixel will be the background color or a foreground color. At the moment, the background color is fixed to black, but the foreground color can be any of the colors supported by the video display controller. So at the top of the screen here, you can see two examples of two tiles, two Space Invader tiles. So where you have a dot, it will be black, and where you have a hash, it will be the defined color. So this tile information is stored in the video display controller's memory, and it is defined by this text file. So each tile is defined by 8 byte values. So each bit within a byte defines one pixel state, either it's black or the defined color. So if you look through this file, you will see that the first tiles define the ASCII characters. So we have 128 of those, and then we have space for 128 graphical tiles. As the first game I wrote was a Space Invaders demo, the first graphical tiles are our Space Invader graphics. And I think at this time I've got around about 60 graphical tiles, so there's space for another 60 odd to be defined for other games. So the way you generate this data string, which defines the 8 bytes that are within a tile, is that you draw this ASCII art representation. And then you can pass that to a Python program I wrote, which will automatically generate this data string that is then used to initialize the memory. Obviously, this data is stored in the video display controller's memory at a certain address, and again, that address value is calculated by the Python program, and that's the address of the tile that you will pass to the software. So you can see for our first Space Invader tile, it's at address 10,112. To make life a little bit easier, I've defined some of those values in a macro file. So rather than using that absolute address, we can use a more human readable label. So if you wanted the address of where the capital A character was stored within the program, you can use capital A _ char. And when you assemble the program, the M4 preprocessor will replace that with the address in the video display's memory. You can see here, so Space Invader Alien 1 in the down position is at address 10,112. So again, to show this software in action, we have a test program 6. And to draw those tiles on the display, we can just use the draw tile macro. So to use that macro, you pass it the color that you want that tile displayed in. So the hashed elements in that graphical representation will be red, the dots will be black. And then the X and Y positions on the display where you want the top left corner of that tile to be drawn from. Again, to simplify the definition of these values, we can use the eval function. So the X position is given by that eval calculation. So each tile is 8 pixels wide. So we've got the value 8 there times an offset. So we're starting to draw the first tile 6 tile positions in from the left. You'll also notice that in that eval calculation there's a 0+ offset. And sometimes it's nice to shuffle around the fonts if the spacing isn't quite right. So that eval function will create a number. It'll create a X position pixel number that the tile will be drawn from. The Y position is fixed, so we'll be drawing all these tiles on the same row, and that's starting at row 78. And again, our coordinate system for our display, the top left corner of the display is pixel position 0, 0, row 0, column 0. And the final thing we pass to our draw tile command is the address of that tile. So B _ char here. And again, if you look back at the macro file, B _ char will be converted into that address within the video memory for us. So you can see what this program does is it prints out the characters Bob Games on row 78, and you can see here Bob is at positions 6, 7 and 8. Then we have position 9 will be blank, and then 10, 11, 12, 13, 14 will be games. And then on row 90 we print out the characters a Mike F production. So like the draw box command, this macro here is passed constants. That is, its XY positions are defined by numbers rather than variables. As always, a slightly out of focus picture of that in action. So I programmed the FPGA board and ran that program, and as you can see, it prints out that text message. As always, the 4 square dots in the 4 corners are from our frame buffer initialization test image. The graphical tiles that define the Space Invaders, again, are displayed in exactly the same way. There's no difference between character tiles and graphical tiles. So to display all 6 Space Invader tiles in their up and down positions, we just enter these lines here, defining again the X and Y positions, their color, and again that label to the address within the video display controller's memory. Okay, as normal, we have my best efforts at trying to take a picture. I think this one's in focus but slightly overexposed, but we can clearly see now we have 2 additional rows of Space Invader tiles. And during the game, we just alternate between these to give that illusion that the Space Invaders are walking across the screens. So the legs in one position and then the legs in a different position. So when you use the draw tile command, the black regions within the tile are written as black onto the screen. So if you were to draw a tile on top of something else, then you would box out that 8x8 region. So all those pixels within there will either be set to the foreground color, in this case yellow or green. The unused regions of the tile will be written as black, which is fine for this example here. So when you've got text or when you've got the tiles and they're not interacting with anything else, that is fine. But if you had 2 tiles that pass on top of each other, so imagine the Space Invaders moving left to right, and if they were to cross over, then obviously you'd see that square box, you'd see that 8x8 square region masking out a tile that was underneath the tile you're currently drawing. And that's not desirable, obviously, in some scenarios. So to get over that one, we have the overlay tile command. Rightio, to show that command in action, we have this code here. So I've added a couple of lines to the end of the program. So now we have 2 tiles drawn on the same line, so on the same row and in the same column position. But they're offset by -2 and +2, as you can see in that eval function. So they're overlaying each other. So if you were to use the draw command to do both of these, then you'd see that hard line, you'd see that black edge of the second tile masking out the previously drawn tile. So in this case here, you'd have the green tile would be masking out the yellow tile's image. To get over that problem, rather than use the draw tile command, we use the overlay tile command. So you can see here for these 2 lines, I draw the first tile using the draw tile command, and then the second tile is drawn using the overlay tile command. So in our previous discussion, when we define the tile, we use the dot to indicate that that pixel is not used and should be the background color, in this case black, and the hash was the foreground color, and that would be assigned the specified color. So the regions within the tile that are defined as a dot are not written to the frame buffer. Only those regions that are defined by the hash, that is an active pixel, are written to the frame buffer. So that means you can overlay the 2 tiles. They kind of merge into each other. You get that kind of illusion of a foreground and background layer. And for this simple video controller, we don't have any concept of layers. We have one frame buffer, and that's what's written to memory. So we have to kind of approximate it in software. And this kind of does that. So another screenshot here, and we can see we've got 2 additional tiles on that top row. So if we zoom in on that, you can see the green tile is overlaying the yellow tile. So the yellow tile uses the draw tile command, and then the green tile is overlaid on top of it. So you can see where you have black regions in the green tile, they are transparent. You can see through the green tile and see the yellow tile underneath. So you can kind of think of this as the yellow tile is in the background layer and the green tile is on the foreground layer. But as I said, there's no concept of layers in the SimpleCPU's video controller. You just have one frame buffer containing the pixel values. So in a game scenario, you might have these two tiles moving across each other. In this scenario, you'd have the green tile moving across the yellow tile, and there'd be a nice smooth transition as these tiles moved across each other. You wouldn't have that hard black edge that surrounds the tile. So if you look at the original artwork for that tile, you can see that there's a leading and a trailing column of dots. So those dots would be obviously the black pixels. So if you were to use the draw tile command, you'd get that hard black edge as the foreground tile moved across the background tile. So in addition to the draw tile and overlay tile macros, there's also subroutines to support that. So if the position and color of your tile changes as the game logic implements the game's functionality, you can call these subroutines and obviously change these variables. So we have the draw tile subroutine, and we also have the overlay subroutine command. In addition to that, there's some additional functionality written in software that allows you to draw digits. So a common requirement is to display a player's score. So here we can load in the base address for the character 0 and then just add on an offset from that to get to the next digits value. So obviously the tiles for the character 0, 1, 2, 3, 4, 5, 7, 8 and 9 are stored in sequential positions. So you can just add an offset from that initial base address. There is also a draw tile function where you can pass it ASCII values. So ASCII characters within the visible range of displayed characters. So from 20 hex to, I guess that's 7, should be 7E hex, as I think 7FX is the delete character, which wouldn't be displayed. But you can send those ASCII codes to that subroutine and it will display those for you as well. Finally, we have a subroutine where you just pass it the address of the tile you want to display. And that will draw that tile at the defined X and Y positions using the base color you've passed in the variables you can see here. So within the video memory's memory, we have a series of tiles defined. The initial ones are based from that Space Invader games, but there's some more generic ones as well. We've got various shapes that we can use to draw various graphical elements. So corners you can see here, lines, branches, crosses, diagonal lines, all useful tiles that we can use to construct simple game graphics. So now we have some basic building blocks that we can use to build a simple game, such as Pong, for example. So we can draw the game graphics, the edges, the borders, the net, the ball, the bat, using the block command. And we can display each player's score using a tile, displaying the digit fonts from 0 to 9. So that's what we'll do in the next video. So we'll input a simple, I'd say, proto game, so not quite a game, but something that shows all the basic building blocks of a ball moving across the screen, bouncing off the walls. Something that can be extended to make a Pong game in the next step. Okay, I will try and get that video done for next week.